Hello everyone, I'm Yinda, and today I'll present our paper, Enabling Silent Telemetry Data Transmission with InvisiFlow. And this paper is a collaboration with Liangcheng, Gianni, Zhang, and Vincent. And let me begin with some background and the motivation behind our work. Modern data center applications rely heavily on the telemetry data to monitor the network conditions and optimize performance. For example, recent advances in congestion control use the in-network telemetry to monitor the switch queue length, enabling fine-grained traffic management. And similarly, path tracing techniques collect per-packet, per-switch logs to reconstruct the flow path, an essential capability for effective debugging. Our load balancers also depend on the real-time link load information to adapt quickly to the congestion, ensuring efficient and stable network performance. However, a major challenge is emerging. The volume of telemetry data is increasing rapidly. As the network events like congestion occur more frequently, finer-grained telemetry is needed for accurate monitoring. At the same time, more applications are relying on telemetry to improve performance, demanding a broader variety of data, from the switch-level buffer statistics to the flow-level packet count. And typically, this data is collected by server distributed across the network, where it's processed, analyzed, and stored. In our work, we focus on the critical component of this system, the transmission channel between the telemetry sources and the collectors. And to efficiently utilize resources, telemetry data often share the same network infrastructure as the user traffic, leveraging the fetch sharing to simplify deployment and reduce costs. And to enable effective coexistence of telemetry and the user traffic, two key requirements must be met. First, the telemetry's sustainable throughput must be maximized. Ensuring zero packet loss, reliable telemetry is essential for network operator to make informed decisions. And even small amount of data loss can result in incomplete or misleading insights. And second, the impact on the user traffic must be minimized. Telemetry should not introduce latency, packet loss, or congestion that could degrade the application performance or user experience. And with these requirements, let's look at the existing solutions and their limitations. And to reduce the overhead on the user traffic, some approaches will compress the telemetry data at the sources using the sampling or the sketching techniques. For example, the sketching algorithm may allow switches to maintain compact data structures, like array of counters that approximate the flow statistics, and then periodically send to the collectors. However, this method often trades the generality for the efficiency. Supporting multiple tasks can still lead to high data volume. And the approximations they introduce can significantly reduce the accuracy. Take Point, a state-of-the-art encoding scheme for the path tracing. It can keep the bandwidth overhead below 2%, but may fail to capture path records for over 60% of flows, particularly those too small to be tracked. And in summary, while these compression techniques save the bandwidth, they often compromise the accuracy. Instead, we argue that enhancing the underlying transmission channel can preserve the data fidelity and reduce the impact on the user traffic. And unfortunately, current transmission strategies fall short on meeting both requirements. For example, the traditional approach of sending telemetry as a standard data packet can interfere with user traffic. Our evaluation shows it can increase the flow completion time by 90%, harming the latency-sensitive workloads. Another approach is to embed the telemetry data directly into the user packet, as done in the in-band network telemetry. However, this technique also introduces notable overhead. Our results show that it can increase the application throughput by 20%. To mitigate it, some systems will prioritize user traffic over telemetry. While it reduces interference, it risks telemetry starvation and packet loss during the congestion, compromising the accuracy of monitoring. For example, our benchmark of a path tracing utility shows that this approach can result in around 11% of paths being missed. So it brings us to a key question. Is there a better solution that can ensure accurate telemetry without compromising the user traffic performance? And in this work, we introduced the InvisiFlow, a communication substrate for telemetry data transmission that's designed to meet these two goals. And I will begin by explaining the core intuition behind the InvisiFlow. And to meet both requirements, InvisiFlow is guided by two key design principles. First, to minimize the disruption to the user traffic, InvisiFlow also prioritizes the user packets, similar to some existing solutions. And second, to maximize the sustainable telemetry throughput, InvisiFlow takes a different approach from the traditional system that may always follow the shortest path. Instead, it actively searches for and leverages spare capacity in the network, aggressively routing the telemetry data through the underutilized link. But it raises an important question: does the spare capacity actually exist in data center networks? And if so, where can we find it? In reality, we found that free network bandwidth often exists in today's data center networks. While the network congestion does occur frequently, where certain links may be fully utilized by the user traffic, many alternative paths remain available for telemetry transmission. And this availability is primarily due to two key factors. First, data center network topologies are typically designed with built-in redundancy to ensure reliability and performance. And second, user traffic tends to be bursty. Recent study shows the congestion is often caused by the small burst, while the average network utilization remains low. Because the telemetry is generally off the critical path for the user-facing request, it became an ideal candidate to take advantage of this underutilized moment in the network. However, prior transmission that strictly follows the shortest path cannot fully exploit this unused bandwidth. As illustrated in the figure, the shortest path between the telemetry source and the collector can be blocked by the user traffic. We have to utilize some longer paths to explore the available capacity throughout the network. But there is another challenge. Given the bursty and dynamic nature of the user traffic, how does InvisiFlow identify this available path in real time? And to maximize the sustainable telemetry throughput, InvisiFlow uses a congestion gradient-based transmission strategy to identify and explore the spare network capacity. The congestion gradient is defined as the difference in the telemetry buffer usage between the neighboring switches. Unlike the traditional forwarding, where packets blindly follow the shortest path to the destination, congestion gradient-based transmission ensures that between any two neighboring switches, packets are forwarding from the one with higher telemetry buffer usage to the one with lower usage. Let's walk through an example to illustrate it. And we regard the collector sinks always have the zero telemetry buffer usage. And as a result, all its neighbor switches will forward telemetry data to it if they have any telemetry buffer usage above zero. Now let's consider the switch with 91% telemetry buffer usage, the highest in the example. It will forward the data to all its neighbors, distributing loads to reduce its own buffer usage. And likewise, other links will forward telemetry packets from switches with higher usage with those with lower usage. This behavior is similar to water flowing downhill, from areas of high elevations to low. It ensures that heavily loaded switches automatically utilize more paths, which reduce the risk of telemetry loss and help maximize the sustainable throughput. Previous scheduling theories have shown this strategy to be optimal to maximizing the sustainable throughput, and is robust across diverse network topologies and the traffic pattern. Well, while InvisiFlow draws inspiration from the simplicity and the effectiveness of the prioritization and congestion gradient forwarding, putting the theory into practice introduced several key challenges. First, congestion gradient-based forwarding requires each switch to be aware of its neighbor's buffer occupancy to compute the gradient. It leads to a crucial question. How can we efficiently collect this information across the network in real time, capturing the dynamic congestion patterns without introducing significant overhead or interfere with user traffic? And second, InvisiFlow assumes real-time adaptation of the forwarding path based on the live congestion data. However, current packet processing pipelines impose constraints. The output port is typically selected early in the processing stage, often before the egress buffer status is available. And this early binding limits the flexibility required for the dynamic congestion-aware forwarding decision. And given this challenge, I will now present the architecture and the implementation of the InvisiFlow, and explain how we have designed the solutions to address these issues. And let's start by looking at how two switches interact in InvisiFlow. As discussed earlier, user packets are constantly flowing through the network. And to operate alongside traffic, each switch will periodically inject the low priority pull request, which includes its current telemetry buffer usage, into the gap between the user packets, and send this request to all neighbor switches. And prior works have shown that programmable switch can generate such low priority packets using the packet generator, effectively utilizing the spare bandwidth between the user packets with near zero overhead. And when a neighboring switches receive a pull request, it will compare its own telemetry buffer usage to that of the sender. And if the buffer usage is higher, it responds by sending back the telemetry packets. And now let's examine the packet processing pipeline at each switch and how the InvisiFlow prevents the telemetry loss within the switch. And we'll focus on two key components, the queuing stage and the egress pipeline. The queuing stage is where the packet draws are most likely to occur, where the egress pipeline is where the InvisiFlow will store the telemetry data. InvisiFlow leverages the egress pipeline because it supports the late binding. As the egress pipeline is shared by multiple egress ports, telemetry packets can carry data from the buffer to the next hop without being tied to a fixed output port. And this flexibility is essential to enable dynamic path selections. And we found that in the queuing stage, and both the pull request and the telemetry packets are treated as low priority traffic to minimize the interference with user traffic. And for the pull request, packet loss is not a concern, since they are regenerated periodically. As a result, there is the lowest priority and the shallow queues are sufficient. However, for the telemetry packets, InvisiFlow aims to avoid any packet loss. And to achieve this, it will use the free ports, such as the recirculation ports, which are typically not used by the user traffic, to forward the telemetry packets into the telemetry buffer located in the egress pipeline. And once the telemetry data is stored in the buffer, the packet itself is dropped. And the collector can integrate into the system by behaving like a regular switch. Specifically, each collector will operate as a switch with 0% telemetry buffer usage. And like other switches, it will send the pull request to all its neighbors. And if the neighbor switch have telemetry data to send, that its buffer usage is greater than 0, it responds by forwarding telemetry packet to the collector. And through this pool-based transmission mechanism, InvisiFlow will enable adaptive path selection. However, we observe an edge case. When there are very few telemetry packets in the system, issue can arise where the congestion gradient remains consistently at 0. For example, as shown in the figure, there's only one telemetry packet at switch S2. And both the neighbor switch S1 and the collector have lower buffer usage, so they will both try to pull the packet. And we can find that the packet may finally oscillate between the switches without making real progress towards the collector. And to address it, we introduce slope to the congestion gradient. In addition to the buffer usage, we also consider the distance to the collector. And with this approach, the device closer to the collector will successfully pull the telemetry packets from S2, and ensures that even a single telemetry packet can efficiently progress towards the collector without getting stuck. And finally, I will show the evaluation results of the InvisiFlow. And we evaluate InvisiFlow through a combination of the testbed experiments and NS3 simulations. And in our testbed, we emulated two tier-lift spine topologies. And we also conduct large-scale NS3 simulations on the FatTree topologies, and with varying traffic workloads. And for today's presentation, I will mainly focus on the results from the simulation. We compare InvisiFlow's performance against two baseline approaches, the default priority UDP and the low priority UDP. And for the telemetry traffic, we also run 4 different telemetry applications concurrently on each switch. For example, we'll use the NetSeer for path tracing and NetFlow for the load imbalance detection. And we first illustrate the trade-off between the telemetry reliability and the user traffic performance. And in this figure, y-axis shows the telemetry packet loss rate, while the x-axis shows the increase in the flow completion time for the user traffic caused by the telemetry transmission. And as shown, InvisiFlow can successfully meet both key requirements, near zero telemetry loss and near zero overhead to the user traffic. While in contrast, the low priority UDP could suffer from around 10% telemetry loss, as its packets are forwarded strictly along the shortest path and are more likely to be dropped during the congestion. And the default priority UDP could lead to approximately a 20% increase in flow completion time, since the telemetry packet compete directly with the user traffic for the bandwidth. We also illustrate InvisiFlow's robustness under 2 different scenarios. And one is the load imbalance scenario caused by the faulty ECMP configuration, and one is the asymmetric topology due to the failed link. And this figure will show the trade-off for the path tracing applications under the asymmetric topology. And we know that the y-axis here represents the ratio of missing paths. And we found that InvisiFlow can continue to meet both key requirements under the topology asymmetries, while the baseline approaches will degrade significantly under these stress conditions. And in conclusion, this paper explores the trade-off between the sustainable throughput for telemetry traffic and the overhead imposed on the user traffic within the telemetry transmission channel. We demonstrate that existing transmission methods struggle to meet both requirements, especially under heavy network load. And to address it, we introduced the InvisiFlow, a low-priority communication substrate that leverages opportunistically sending and congestion gradient. Our experimental result shows InvisiFlow can support high sustainable throughput with minimal impact on the user traffic across various applications and scenarios. The source code for InvisiFlow is now available on GitHub. And that's all for my talk. Thanks for your attention.